Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 7 in the relaunch of the channel, and today we're going to talk about how do we know why climate models underestimate reality. So this video is really part of what I call the Titanic series. So when I relaunched the channel, the first video just talked quickly about how I'm doing these videos and the techniques I use, etc., and why and my background and stuff like that. But video 2 is probably the most important video I'll ever do on this channel. And it's titled, What's Our Current Path? The Titanic Table. And in that video, what I did is I went ahead and sort of said, based on my understanding of what the scientific community is telling us and all the information I can gather, here's where we're at. So at different temperature levels, what's our current actual temperature? And then when are we projected to get to different temperature levels frequently talked about by climate scientists. And they talk about it in terms of anomalies from the pre-industrial age, from 1850 to 1900. And they talk about it in terms of 1 degree Celsius, 1.5, 2, 3, and 4 degrees Celsius. And so I showed you in that video when the climate scientific community says we're going to hit these various different levels. And then what are the implications of that? What happens when we hit those levels? And so that's what went on in video 2. It's sort of my assimilation of everything I could tell from doing the research and trying to put it into a concise table so you can understand what's really happening. But then to support that, I said, well, people have a bunch of questions. So where do these numbers come from? How does this all work? And so that's where these companion videos come into play. And so in video 3, I talked about how do we build the climate network, how the various different countries around the world work cooperatively together to get the raw data so we can calculate actual temperature and do these projections. Video 4 talks about how we actually do calculate global temperatures, and there's I think 7 worldwide recognized entities that do that. And then what I did in video 6, I said, well, let me take the most sophisticated one of those and let's do a deep dive into that to show you exactly how they go about calculating actual temperature. And then the next thing I thought I wanted to do is talk about, okay, so we got these climate projections that are out there. Well, sort of what are they saying? What's the process? How's that work? And this companion model is now going to talk about why these climate models consistently underestimate reality. So when I did video 5, I had 4 questions we addressed. And that was sort of, what organization is their organization? What organization? How are they funded? What's their process? Where do they get the raw material from to do these kinds of calculations? What kind of review process takes place? All those kinds of questions. So this video then is going to address the other question, is why do these highly sophisticated climate models consistently, I mean consistently, underestimate the real world pace of temperature acceleration? And so that's going to be the purpose of this video. So now back to a quick snapshot of the Titanic table that we've shown in all these other videos. And what I've done here is I made the border dark, and I bolded the portion of the table that we're going to talk about in this video. So we're going to talk about actual temperatures, and we're going to talk about projected temperatures that are coming from the climate models. Now, in video 5, where we talked about the projections, this was one of the slides we pulled from that particular video. And what it does here, it shows the 5 scenarios that all models ran. There were basically 50 modeling centers and about 100 models around the globe on all 6 continents that really sort of did these kinds of projections. They all ran the same scenarios, etc., and things like that. And they really had what they call shared social economic pathways. And that's what the SSP1 would be, is that's 1 pathway, 2 would be 2 pathways, etc. Then the numbers after that would be, they make different assumptions then, and also independently about what the level of greenhouse gases are going to be in the atmosphere. And they have levels from very low, which would be the 1.9. They talked about it, one way to think about it is in terms of bedding covers. Okay, one could be a thin sheet, 2.6 could be like an autumn blanket, and then down to 8.5, which would be like having a heavy duvet. And so I listed the various, the titles for the various different scenarios up there, and then we went and showed for each one of the major classifications that they use for temperature increases, like 1.5 degrees Celsius to etc. For each one of those columns, I showed when the different models project we would hit that level. So if we take a look at SSP1, 2.6, that's the second row down in the table, you can see that it came up with, we hit 1.5 at 2 in 2030. We hit 2 degrees Celsius in 2050, and we never cross, we never get to 3 or 4 degrees Celsius. If you went to the bottom row, or 8.5, which is the climate skeptics are in control, we would basically hit 1.5 degrees Celsius in 2030. We'd hit 2 degrees Celsius in 2040, 3 degrees Celsius in 2055, and 4 degrees Celsius in 2075. And if you look up above at those columns, you see some numbers that are bolded there. It's the bolded numbers that I took and transported that information into when I constructed the Titanic table. Okay, so that's where those numbers came from. And then you'll notice the 1.5 column is sort of highlighted in blue. And that's because I just want to talk about that in a second here. And then we go back to the Titanic table, and you can see the numbers carried over as I indicated, but you also see a blue section here on the 1.5 level. And what I'm saying on this table is what the people who calculate actual temperature are telling us, is that we hit 1.5 degrees Celsius in 2024. Not the 2030 to 2035 that the climate model said. Now, let's go talk about this 1.5 degrees gap. So in the Titanic table, as I mentioned, the 7 models that calculate actual temperature said that we hit it in 2024. And I've got there right below there when AR6, which is the assessment that was done, projected that we would get there in a range between 2030 and 2035. But there's a significant difference that you understand between the calculations that are going on here, okay? So for the actual people, what they do is they take a 12-month moving average. So they say the 12-month moving average hit in 2024. The projections use a 20-year moving average. So as a result, just that because of that calculation, you'd see a significant delay, okay? But the other thing they do is that when they do that, and the model actually hits 1.5, then they go back 10 years and they say that occurred in that year. And if you think about it, that mathematically makes sense. I mean, if you're going to get the 20-year average to hit 1.5 degrees Celsius, that means you probably hit it. If you took a 20-year cycle from 2021 to 2040, you'd probably hit it about 2030. And it should be above that in the other years, and would take really 20 years before the average got there. So while the average will then hit in 2040, they will say in 2040, by the way, 10 years ago, we basically hit 1.5 degrees Celsius. So that's how this works. And it accounts for a lot of the gap, the difference there that you see. Now, so what we're going to do is we go ahead and compare these climate models with what's actually happening in the world, and I'll call that a velocity gap. I've identified sort of 10 major reasons for those gaps. 5 of them deal with institutional and structural gaps, and 5 of them deal with physical, sort of Earth system kinds of gaps. I'm going to talk about those in groups of 5, so that's why I have the first institutional and structural gaps bolded at this point. So let's go through those one by one, and then we'll proceed to the physical ones. So gap number 1. I call this the curse of the AR6 7-year cycle. AR6 stands for Assessment Report 6. That's when Under the IPCC, all the countries of the world come together in this 7-year massive effort to jointly come up with a calculation of what temperature projections are going to be in the future. Now, that basically was started in 2015, and it issued a report in 2023. Give you a sense of how this goes on, okay? And at that time, quite frankly, temperatures were at 1 degree Celsius, basically, or slightly below that. Now, the other thing that happens now, if you look at it, they really use these climate models. And the climate models are really constructed several years in advance. These are really major, complex things. And in order to participate in this project, you need to be approved. And once your model's approved, it's locked down. You can make no changes to it. So that means most of the work on these models were done 2 or 3 years before, the final lockdown. Now, there's some fine-tuning is going up, and maybe even into the first year of doing the cycle. But basically, these models are fundamentally created before then. So you have an additional gap that occurs here. And so the models are probably based not on information in 2015. They're probably based on information on, 2011 and before. Now, what's happened is since that time, you've had just this massive data explosion. And why is that? Because we've put up substantially more satellites and some other kinds of sophisticated devices like Argo buoys and other kinds of things that we talked about in video 3 to really capture what's going on. None of that information is available for these people when they created these models. So you have this, that's the curse of the 7-year gap. It's not that these people aren't brilliant, they're the smartest people in the world doing this stuff. It's just because of the time it takes to do this, there's just this natural lag. And then the other thing, and if you listen to the video when we talked about how they do these projections, they have these working groups, okay? And remember the Titanic table when we talk about the repercussions of hitting these different levels. What happens when we hit 2 and 3 to 4 degrees. I got that on the next slide, so we'll talk about this refresher a little bit then. But what they do is they have an independent group of scientists that are for multiple backgrounds from around the world, the kinds of expertise you'd want to have doing this, okay? And they go by and they review all the research that's out, and they basically say, here's what's going to happen at that point in time. The problem is that research, probably sort of like the models, is got a lag time associated with it. And so what comes out in the report of 2023 as representing what the client thinks is based on probably a knowledge that existed maybe 2012 or something like that. Maybe, there's some more current stuff, but it's pretty old data, and there's a lot of additional information we've picked up in the meantime, okay? So they've got this 20-year moving average that we talked about, and we talked about how they do the calculation on the midpoints, okay? So why, you're probably asking, so why would climate scientists do that? Well, it really is a really good reason for doing that. And one of the reasons, the main primary reasons, they're trying to filter out short-term noises and the impact of multi-year oscillation cycles. An oscillation cycle would be, for example, El Nino and La Nina. It has a huge impact where we are in that cycle and what our temperatures are. If you look at actual temperature graphs, as we've shown in many of my presentations, you'll see they have the temperatures go up and down every year. Why is that? It's really primarily driven by the El Nino and La Nina cycles. Huge impact. And so if you want to sort of report what's happening, you try to get all that, what they call noise, out. So that's why they use the 20-year moving average. That makes perfect sense from that perspective. The problem is, on the other hand, there's some trade-offs from doing that. And one of the trade-offs is you don't report that you've really reached 1.5. The models say, okay, we're going to reach 1.5 degrees Celsius between 2030 and 2035, but they won't report that to 2040 or 2045. Now you have, and we actually hit it on the 12-month cycle. We actually hit it in 2024. You know, like a 20-year gap. You know? um, and the same thing's true of 2 degrees Celsius, 3 degrees Celsius, and 4 degrees Celsius. Okay. Now, what's important here is these differences are significant. Okay. I mean, take a look at what they say happens at 2 degrees Celsius. The world will see catastrophic and likely irreversible damages. That means there's maybe nothing the human race can do to prevent us from just having temperatures continue to accelerate to 3 and 4 degrees Celsius and potentially higher. That's significant. Or that at 3 degrees Celsius, we're going to be living in a nightmare scenario. And that could occur as early as 2055, but they won't tell us about that to somewhere between 2065 to 29. I mean, you understand the problem? Okay. Now let's talk about the silence breach, okay? Now, because they use this retroactive thing, we really don't know about that until after we've hit it. And so what happens here is that there's really probably, well, we hit 1.5 degrees Celsius in 2024 based on a 12-month moving average. Basically, hardly anybody even knew that that happened. That was not a well-publicized event. Why? Because a lot of the scientific stuff that people want to use is they look at the 20-year moving average. And they don't understand the difference between these two. They don't understand the impact of the fact of how far these models lag behind reality. That there's probably no mainstream public awareness that we hit 1.5. Now, that's not too frightening at 1.5. Okay, I get what I was going to get a little worse stuff like it is absolutely very frightening at 2 degrees Celsius when you say that the human race will lose control, or at 3 degrees Celsius where we're going to be living in a nightmare scenario. Being unaware of that is frightening. And so as a result of that, we're just not aware of that. We have a false sense of security, I guess, of what the future looks like and the amount of time we have to really react. Now, the other thing that happens, you have this sort of institutional hesitancy or gatekeeping kind of processes to some extent. One, you always have the climate deniers and other things that are, have a different agenda. And so they will quickly criticize things if you don't have documented evidence. So what happens is that you want to make absolutely sure you know what's right. So therefore, nobody really wants to talk about the fact that 12-month moving average there. They want to rely on a more reliable 20-year moving average because that's what everybody talks about. And they probably don't want to release even other related things too soon unless they really absolutely know that they have the information is absolutely bulletproof. And that can take time. So that delays, again, the frequency with which people get knowledge of what's happening. The other thing is a lot of this stuff really ends up behind what they call paywall journals or in technical journals. Now, to get an article in a technical journal, it has to be the article's got to be written, the research has to be done. And it takes a while from the time the research is done to do the article, and then it's got to be peer reviewed, and it can take months to years before it actually gets into one of these paywall journals. And so the public doesn't really get access to that information either. And even when it hits the paywall journal, it's already probably 2 or 3 years, maybe even 4 years behind what potentially the reality can be. the other thing is, so let's talk about another trade-off. So we have the IPCC report, and I talk glowingly about the IPCC in video 5, and how all 95 nations have to agree on a line-by-line basis of what's in their assessment report, which is done in a 7-year process. And that adds incredible credibility to it. Why? Because you get these checks and balances. That means that the energy-producing greenhouse gas or fossil fuel-producing countries have to agree with the language along with those people that are being impacted by that, and that everybody has an equal vote. Even some remote territory in the Pacific that could get flooded. And so as a result, coming out of there, you have a very, very credible document, and I think that is incredibly powerful. But you also need to, indirectly, what happens though is you get sort of a dilution, right, that occurs in terms of urgency, and delays and signs of real time warning that we've got a crisis on our hands. And so you end up with sort of this collective hesitancy to really tell us what's going on in the world, okay? It's a natural process, and I'm being critical of anybody. I'm just saying we need to recognize that. And so the world's sort of missing this real-time warning apparatus, and so most people really are having trouble struggling with this, which leads to this last one, which is the complete political and I think even public disconnect with the reality of what's going on here. And the political people spent so much time on 1.5 degrees Celsius by 2050. Right, that was the big push. Why? Because they didn't think they'd be able to get there by then. And by focusing on that, it put it out, 30 years or so, and it gave us time to deal with the stuff and deal with the political structures and all those kinds of things. But everybody, and we talked about 2% happening at 2100, and people don't distinguish between much. There wasn't much done to distinguish between how this is not linear. It's logarithmic, is what I'm trying to say, and that what a significant difference there is between 1.5 degrees Celsius and 2 degrees Celsius in terms of what the implications are. And maybe there's some right. There was no discussion whatsoever around the globe about 3 and 4 degrees Celsius, what happens at that time, and yet these models are suggesting in some cases we could get there by 2065, which is really, remember, we won't know about that, the 2075. I mean, people just aren't aware of the risk here that's being involved, and so as a result of that, we're trying to do things, we're engineering to get to 1.5, we're doing things. The solutions we're coming up with are going to be totally inadequate for 3 degrees Celsius or 4 degrees Celsius, etc. So we have this huge disconnect between what's really happening in the world and these sort of linear projections. So now let's get to the next group of gaps. And now we're get to the physical Earth system gaps, and let's get started on that. So we have the unmodeled physical drivers. Now, because of this gap we talked about between when the models were created and where we are today, there's probably 3 major events that have happened that aren't at all, probably, or not in any meaningful way reflected in the models. There are some other major ones like Arctic amplifications and other things we knew about, so some of that got reflected in here. But nobody really anticipated the Arctic albedo collapse. I mean, they knew what the impact would be if ice melts, but nobody really picked up the pace at which this is happening, okay? So what that means is sea ice sort of melts, and as it does that, it's normally white, and what that did is that reflected sunlight back into the atmosphere as shortwave radiation, and it didn't affect our greenhouse gases. Instead, what's happening as the surface gets darker, it gets absorbed in the Earth, and it gets radiated back at long-wave radiation, and that interacts with greenhouse gases. And there's been a massive amount of of Arctic sea ice collapse in the last 10, 12 years. And the models just didn't pick that up. Another thing that's happened is that we passed some clean air resolutions with regard to shipping. IMO 2020, which dramatically reduced the amount of sulfur pollution in the atmosphere from shipping. That's great. Great idea. Why is that? Because all the sulfur was causing a very acidic ocean, and it's a significant impact on human health. But there's a side effect. There's all these things, okay? One of the things, the side effect of that, though, is that one of the things that the sulfur particles, when they did, when the sunlight hit them, they would reflect it back into space, so it looked like a metal. Now that we're cleaning some of that up, more of the sunlight is hitting the ocean. And it's getting absorbed into the ocean, and so ocean temperatures are rising faster than the models had projected. And then the other thing you have is what they call the carbon sink paradox. Models understood what happens, that trees and forests act as carbon sink pull. That was well known. And if the if the size of the forest shrinks, then the amount of carbon pulled out of the atmosphere will affect it. And there's also a reverse negative effect. Not only is it not pulling carbon dioxide out of the atmosphere, what it's doing is as it burns and decomposes, or other activities take place there that generate greenhouse gases, it actually causes an increase in greenhouse gases there, okay? I mean, they understood the concept of that. Nobody in these models back then appreciated how fast our forest would be shrinking, how fast the Amazon rainforest has shrunk, which is the world's largest one. Look at all the forest fires in Canada and over the United States and other kinds of things in Europe and other places. So these huge carbon sinks are shrinking rapidly, and the models didn't pick those up. So those three blind spots are will account for some of the gap we're seeing. It's not reflected in these models. Now, the next version of the models will hopefully incorporate some of that, but then there'll probably be another set of new conditions they're not keeping track of, okay? Now, I've shown this slide many times in other presentations, so I'm only going to talk about it for a second. The Earth is composed of 5 major spheres. The atmosphere, which is air, the hydrosphere, which is water, the cryosphere, which is ice, the lithosphere, which is the surface of the Earth and below, and the biosphere, which is living things on Earth and in the oceans and things like that. And all of these subsystems, these spheres have subsystems. We've identified the major subsystems on this page. And these subsystems have tipping points, which we've talked about in the past. And what I showed here on this graph is when we hit 1.5 degrees Celsius or below, all of the systems in red will have been in their tipping range. When we hit 2 degrees, all of the systems in green will now be in their tipping range, and the black is those that are above 2 degrees Celsius. If you take just step back and look at the picture, we weren't going to delve into this in a lot of detail. Just look at it. What does it look like? It looks like Christmas time, right? There's so much red and white there. So if we're already at 1.5 and we're moving rapidly to 2 degrees Celsius, the tipping of all these systems is going to have a dramatic impact on us. And I'll talk about that in sort of the next one here now. And I'll call this self-sustaining feedback loops. So if you take a look at the first bullet up there, take a look at the table in the right-hand corner. What I did is I summarized the information from the prior graphs. Just take a look at this one. At 1 degree Celsius, basically 16% of Earth's subsystems were in their tipping range. At 1.5 degrees Celsius, 60% of Earth's tipping systems are within their tipping range. At 2 degrees Celsius, we're up to 88%. I mean, basically all of them almost. I mean, so you see how close we are to really just having a massive impact? And nobody's talking about it. Now, let's talk about what can happen here is you have this sort of self-sustaining feedback loop that can occur. And what that means is that the physics of Earth's physics of that particular subsystem sort of take over and just cause a physical chain reaction. And it's probably nothing human beings can do to prevent it. It's not human-caused temperature increases that are impacting anymore. It's sort of the physics that's taken over, okay? Let's take a look at the Greenland feedback mechanism. This is not the complete feedback mechanism. This is just a few items just to get the point across. Greenland's an ice sheet, right? And the ice sheet and it's also kind of a mountainous range to some extent. And so what happens is that when we had higher temperatures, it would melt down. And then the following winter, it would sort of go up a little bit, only it didn't go up as far as it did the previous year, and that goes on year after year. And what happens, that's because the temperatures are lower. Lower you get in altitude, the warmer the area gets. So you have higher temperatures going on, even in wintertime, relatively, okay? And so that has an impact on it. And the other thing is what happens as it does that, it creates these pools of water. What's the unique characteristic of water? It's dark. And so what we had before is we had white ice, which reflected. Now you have these dark pools, and you have these dark pools, they sort of absorb it, which accelerates warming. So what happens as you go down farther every year, the pools get bigger, right? We get more absorption. It sort of accelerates that, which further brings the level down. And you got this cycle that just keeps on going on and on. It just sort of feeds on itself, okay? And it's very hard. These gaps, these models sort of take that, at least particularly back then, as sort of linear sort of events. They couldn't take, they weren't able to calculate or create their models such to take into consideration these feedback or exponential kinds of things that are going on. Maybe when they do the next set of models, this is pretty well understood now, maybe they'll be able to do that, but those models are probably being created right now, but probably the next assessment report won't be to probably maybe 10 years from 2024 or 2034 or something like that. And by then we may have the same problem. We'll be at 2 degrees Celsius in terms of the actual by the time the model comes out, okay? So let's talk now about the domino effect. So when one of these subsystems behavior changes, as we talked about in the previous video, it doesn't just affect itself. All these subsystems of Earth system are all interconnected, and they influence the behavior of neighboring systems. Let me give you just a quick example. And again, this is incredibly simplistic. There are infinitely more impacts on this that I'm going to talk about here. This is a very simplified version, okay? But so the Greenland ice melts, okay? What happens? It all goes into the ocean. What does that do? It reduces the salinity of the water, ocean water around Greenland, right in the Atlantic. Why? Because sea ice doesn't have salt. When you freeze water, the salt's gone, okay? Now, what happens now is that, so as it reduces the salinity, it reduces the flow of the AMOC. One of the things that drives the AMOC, that causes it to go from the surface to the bottom of the ocean and down and back towards Antarctica, is the density of the water. What causes the water to be dense? Well, it's getting colder, but it's got all this salt in it. And so as a result of that, it starts slowing down. Now that in turn affects, as we talked about previously, that affects all kinds of systems around the world. One of the things that could affect is the monsoon season. And the monsoon season will then affect one of the monsoons that would get affected eventually would be the South American monsoon, which then will affect the behavior of the Amazon rainforest, and it could cause it to further accelerate or die back faster. Because these models sort of deal with linear, they may be able to do some things to deal with maybe a feedback loop to some extent, probably crudely and in AR6, maybe in a more sophisticated way in the next version of that. It's almost impossible for them to fully take into consideration these multi-system interactions, because these are very complex things. And to do the research necessary to identify all those things takes years. And so what you end up with is this velocity gap. They're not taking into consideration the multiplier things that are destabilizing, which will cause our real-world behavior to just accelerate even faster than it has in the past. It's not linear, it's logarithmic. And that's why. And so let's sort of wrap up this gap. And this is the compounding impact, as I call it. Because we've got these 10 gaps, okay? They're not all isolated gaps. They we talked about the domino effect of our subsystems. They all sort of interact together, too. And they simultaneously result in administrative delays, outdated math, human policy inertia, active, so we have planetary cascades that are taking place that people aren't aware of, etc., and things like that. And we don't really pick up the fact that we're really dealing with a logarithmic kinds of impact. And these impacts are really, really serious in terms of what living conditions are like on Earth. And sort of the strategic imperative here is we sort of need to shift our focus. We need to recognize that we're dealing with this real-time risk. And it's acceleration here. And we need to start building in and dealing with ways of dealing with that, building in resiliency and doing other kinds of things, okay? So that sort of wraps it up. Let's go back to the Titanic table here. Now, we talked about what actual temperatures are. We're in 2024. We talked about how the models were different. We projected that to occur between 2030 and 2035. But that was based on a 20-year moving average. And we talked about their projections for the future in terms of when we get to 2 degrees, 3 degrees, and 4 degrees Celsius, right? And then we talked about, just briefly, I want to mention again, I guess, what happens at these different levels. Because I think this is the thing that we're just fundamentally missing. We're in a linear world, and we're having trouble, I should say we're in a logarithmic world in terms of what's going on real time, and we're having trouble even thinking about it in terms of a linear world. But these numbers are just around the corner. Look at 2033. If we just follow the 9-year extraction, we'll be at 2 degrees. It's continue that same thing. It would be at 3 degrees in 2051 to 2069. And to some extent, some of the models have us to some extent in some of those range too, with more serious things. So I guess I'm just trying to say we just need to appreciate the models are really good that we have, but there are some concerns and drawbacks. And the numbers you're seeing here for projections from the climate models, if anything, are probably dramatically understate the pace at which temperature increases are going to occur. So let's wrap this up. We talked about the 10 gaps and how the models sort of underestimate reality. The other reality is that the only way to prevent really just a disaster for our kids and our grandkids and other things is we need to get the net zero greenhouse gases, and we need to do that now. What are some action steps? Well, one, we talked about this frequently, voting. We have election coming up here in 2026 when I'm doing this video. We also have, ongoing elections. And I think at every level of government, we need to elect officials who believe we have a climate crisis, the science is real, and are willing to do something about dealing with it. Now, if neither candidate has it, then I would say just vote the incumbent out because they had a chance. Maybe you can influence the other person, But this is a real problem. We need to do so. The other thing you can do is subscribe. If you rate this video, it might help with that. But share the link with other people in your family and people you know and friends and say, hey, listen to this guy. This is a real problem I think we have here. We need to start talking about this. We need to start building up a consensus from the bottom up that says, yeah, we have a real problem here. Wake up, folks. Wake up, leadership. Because if you're waiting for a top-down solution to this problem, it's never going to happen based on what I can see of our current leadership around the world. And then take personal action in other ways you can. And join us for other videos. And again, I really appreciate you taking your time to listen to this video. If you have any suggestions for other videos I ought to do, please let me know. So far, most of my videos have focused on the science, and that's because I really need to understand what's going on to talk authoritatively about it. Some of the new videos I'm going to create, I'm going to do a bunch of videos because I've got them canned in terms of science stuff, but I'll also start talking now about pathways and consequences of what's happening. So thank you very much, and I hope you'll join us for other videos.